Hello, everyone. Today we're going to be talking about molecules. Yay! It's finally time for some real chemistry. So, really, what we're going to be talking about is chemical formula in general. So, one of the big things about chemical systems is that most of the time we're looking at combinations of different elements in specific ratios. And these make all of the various objects we're familiar with. So, a good place to start is our good old law of definite proportions. And this is just the idea that a chemical compound is always going to contain the same elements in a fixed ratio. So, whatever the compound is, whatever the molecule, it will always have the same elements in the same molar ratio. And so, these ratios give rise to what we call an empirical formula. And that's really what an empirical formula is more or less just the ratio of each element with respect to each other. Maybe not the total amount of each element present, just their relative numbers. And this can be used to describe both individual molecules and large solids, which is one of its big advantages. So you can have something like formaldehyde. So formaldehyde is a specific molecule. It contains one carbon atom, one oxygen atom, and two hydrogen atoms. And you probably know it for, well, preserving things. So anytime you have dead tissue, whether it's a person or a squid, no matter what, it's always going to be the same molecule, this same ratio. In contrast, we have something like cuprous oxide. So cuprous oxide actually forms a larger solid. And so what we have here is a large system of copper bound to two oxygen atoms, and every oxygen atom bound to four copper atoms. And this gives an overall ratio of twice as much copper as oxygen. And all cuprous oxide will have this same ratio. However, I can't just isolate these three atoms and have an object. So this is one of those things to keep in mind. Sometimes we form molecules, sometimes we form larger ionic solids. So one of the big things is if I'm going to deal with these molecular systems, so specifically focusing on the molecules because they're a little easier to deal with, all we have is the ratio of atoms. That's fine for a solid, but for a molecule, I need to know the total number of atoms because that can change a lot of my associated properties. There are plenty of molecules that have the same uh, ratio of elements, but very different overall species. So this is called, so if we include the total number of each atom present, we generate what's called a molecular formula. So one of the reasons why this is important is there's a lot of molecules that share a single empirical formula. So let's go with that empirical formula for formaldehyde we had earlier. Twice as much hydrogen as carbon, equal amounts carbon as oxygen. Well, that's formaldehyde, but it turns out that's also acetic acid. One is deadly. It preserves tissue. You drink it, it will preserve you. No bueno. Acetic acid, however, well, that's vinegar. And so you'll notice that they both have the same ratio of elements, but it matters a lot more that we have twice as much of each of the elements. So it's fairly important to be able to denote molecular formulas, though a lot of times we have to start with empirical formulas first. And then we can try and pull a couple of tricks, which we'll talk about later, to back out the molecular formula. However, when we're writing molecular formula, we also kind of need to figure out how to write it. So when I have, say, acetic acid, I have three different elements. Well, which element do I write first, second, or third? And what other features do I need to have? So first things first, if there's a metallic element present in your molecular formula, write that one first. So if I have multiple metals, like say cobalt and iron, we're going to write the metal of a lower period first. And if they're in the same row, like iron and cobalt, we'll write the one further to the left. This is also known as writing the more metallic species first. And as you go down and to the left on the periodic table, you have a more metallic species. And we'll talk about this much later. However, most of the formula we're going to be dealing with for now are only going to contain either a single metal, and a lot of nonmetals. So when writing nonmetals, we're going to try and follow a general formula. So carbon goes first, then phosphorus, nitrogen, hydrogen, sulfur, uh, all iodine, bromine, chlorine. So most of our halogens. Then oxygen comes in right before fluorine. And there is actually a logic to this, and it's based on how much each of these ions, of these atoms want electrons. But we're going to have to get into periodic trends, which we'll do somewhere about in the middle of the semester. But for now, just kind of remember this overall arching trend. In general, the more left you are on the periodic table, the more likely you are to be written first. Lower you are on the periodic table, more likely you are to be written first. And that's exactly what we're seeing in these general trends. With a couple of anomalies, I'm looking at euhydrogen. So this tells us the order in which we're going to list our elements. Metals first, then we work through our nonmetals, generally left to right. However, we also have to deal with the fact that not all elements are present in equal ratios. So we can also use subscripts to denote the relative number of each element in the molecule. So if I'm looking at water, it's got two hydrogens. So I have H subscript 2, denoting I've got two hydrogen atoms, and oxygen, no subscript. If I have no subscript, it pretty much means that I have a de facto subscript of 1. And this actually works fairly well for most molecular species. However, we do occasionally run into a phenomenon known as a polyatomic group. So this is essentially when I have a series of atoms that all kind of form their own set molecule within my bigger molecule. So this gets a little messy, and we'll see some of these as we show up. But a good example of this is something like water. So I may have something called copper sulfate, but I have 3 waters around it. The waters are an individual set of molecules, and I've got 3 of them. So I'm going to denote that I've got 3 water molecules, which gives me a lot more information than simply saying I've got 3 oxygens and 6 hydrogens, which tell me very little about the structure. So again, if you want to denote that there is a specific group that moves as a group in your molecular formula, use the parentheses and then a subscript to tell you how many. So one of the phenomena we have is, just like there's plenty of chemical species that share the same empirical formula, we're also going to have a fair number of species that can share the same molecular formula, especially if you end up going on next year to organic chemistry. Organic chemistry is kind of infamous for this. So as a result, one of the things we often teach you how to do is writing structural formula. So this is going to be an arrangement of atoms linked by bonds, which are essentially ways that electrons hold our 2 nuclei together. And there's going to be multiple ways that we can convey these basic structures. The simplest, the one that I'm going to tend to use a lot, and we'll show you how to draw them much later, is a line structure. So it shows all of the elements present, and if they're held together by electrons, we denote a bond. If I've got 2 lines, this means I've got a double bond, and I have twice as many electrons holding these 2 atoms together, making it a tighter structure. And so line structure is a fairly easy way to convey the form of a species. So we're going to tend to use a lot of line structure. There's also another method called ball and stick. This is often used for 3D models, where you literally have balls and sticks, balls representing each of the molecules. There tends to be certain color coding. Hydrogen is almost always white, carbon is almost always black, oxygen is almost always red, and nitrogen is almost always blue. After that, you have to be a little careful, as a lot of people have different conventions. And so this lets us use things like model kits, which we're going to again play around with a little bit later this semester. Finally, the last form that you'll often see, this is often in computer modeling, is space filling. So it has the same information telling us how all of my atoms are held together, but what it really does is help show the overall size of each of these atoms. Because let's be honest, if I have something like a line structure or ball and stick, it makes it look like most of this area is open space. Well, in most of this area, we're going to have a lot of electrons moving around. So we often convey the individual size of each atoms using this space filling model. Each one of which gives you a slightly different view on the system. We're going to tend to use a lot of line structures just because of their ease of use whenever a simple molecular formula isn't good enough. However, one of the ways that one of the important things is going to be trying to figure out how to write a structural formula by hand that does give us some of this information we got from the molecular formula. For example, if I just say that this system is C2O2H4, I lose a lot of information about my acetic acid. So one of the things we can do to kind of bridge that gap is to use what's called a condensed structural formula. So what we do is we're going to take each of these little subgroups and write them each independently. And as we link them together, it tells you where each of these atoms are located with respect to each other. So what we're essentially doing is writing each of these nodes as a condensed molecular group and then tying them together. So if I have acetic acid, I have CH3, C, oxygen, then an oxygen linked to a hydrogen. It is worth noting that if you do have this group where I've got a carbon with two oxygens, it's often denoted as CH3CO2H. So both of these are the same things. This formula, however, makes it very clear how these atoms are arranged. So this is something to keep in mind, and we'll be seeing this as we go forward later when talking about organic molecules. All right, so next time we're going to be talking about a specific subniche of molecular species, the elemental molecules, where I have a molecule that's made out of just one element. Until then, until next time, take care.